Welcome to this lecture in which we will solve LQR as a boundary value problem. We will formulate this problem as 2-point boundary value problem and solve it using the sweep method of Bryson and Ho. Recall the problem formulation. Our objective function J prime has to be a minimum with respect to u, lambda and x. J prime is given here. We differentiated with respect to u and got this expression. We want that to be equal to 0. We differentiated with respect to lambda, got this expression that should be equal to 0. Finally, with respect to x, we get these three equations. Notice that this lambda comes inside this bracket. So as a result, lambda also will be a vector, lambda 0, lambda 1 and so on. X of 0 is known because that is how we start our state space equations, but lambda 0 is not known. So we cannot march forward. So let us start with the three equations we derived earlier by differentiation. We called these as control, state and adjoint equations. Lambda 0 is unknown, we cannot march forward. We will demand that u of n to be equal to 0, that is kn equals 0. Control law k at time instant n is equal to 0. Notice that we are calling k control law as a function of time. In fact, we will see the control law not to be a constant in this lecture. It will vary with time. Because un equals 0, we see kn equals 0. Also, whenever I write something in red, then that means you have to note this down. We are going to recall this, and if you write it down, it will be a lot easier for you to substitute. Now, I demand that un equals 0. If not, what will happen? Because of this un, the next state, namely x of n plus 1, will be non-zero because this is not 0. If x of n plus 1 is non-zero, then this index will have a non-zero term at n plus 1, whereas we are summing only up to n and we are saying that we should minimize this. How can we ignore the term at n plus 1 that is non-zero? So what we will do is we conclude that minimization until n alone is not okay in this objective function. In other words, if this is not satisfied, un equals 0 is not satisfied, this objective function itself is incorrect. What we will do is we will choose n to be large enough so that un equals 0, and then all the problems that we discussed here will not happen. With un equals 0, what happens? From the control equation, substitute un equals 0, you see that lambda t of n plus 1 equals 0, I have substituted k equals n. Now substitute un equals 0 in the adjoint equation. Substitute lambda n plus 1 equals 0 in the adjoint equation. So this term goes away, I get lambda of n equals q1 into x of n. Remember, this q1 is symmetric. So this term is 0 and then we take transpose of this and arrive at this equation. This and the condition on x0 makes it a 2-point boundary value problem. x0 is known, lambda n is known, so this is a 2-point boundary value problem. We can get a direct solution. Let us start with these equations. Recall the boundary condition on lambda n, which is q1 x of n. From the structure of lambda, we will guess a form for lambda. we expect a solution of this type, lambda k equals sk lambda k. It looks like this. In fact, from this we see that S of n equals q1. Please write this down also. So the control equation becomes, with this, transpose of this is q2u, and then bt of lambda of k plus 1 equals 0, and in the place of lambda I substitute, in the place of lambda I substitute s into x, so I get this. From this I get the solution as q2u to be equal to minus this entire entry. Okay. In the last equation we substitute for x of k plus 1, so we get axk plus buk coming here, but for this equation is the same as what we derived in the previous slide. So let us bring uk term from here to the left hand side, I get this equation. Take this to the right hand side, I get the expression for u. Now we will define the terms inside the bracket to be r, and finally we get this expression for uk. This is going to be used again, so I am writing it in red. So this whole thing is r inverse times this bt sk plus 1 axk, which is what I have got. And what is in red is nothing but control law, kk into xk. So this expression will be used in later slides. Now we will arrive at a discrete Riccati equation. What is this? It will become clear as we proceed. Recall these equations. This is the form of lambda we assumed. This is the expression for u we derived in the previous slide. This is what we called as k, and this is the adjoint equation. We started with this. So we write lambda k, take the transpose, take it to one side, say left hand side, and you have these two terms. So we have at into lambda, which is this, and then q1 into x, I have got this. Now express lambda in terms of s using this, except that we have to do this for lambda of k plus 1. So lambda k becomes sk xk, lambda of k plus 1 becomes sk plus 1 xk plus 1, and everything else is the same. And in the place of xk plus 1, substitute from the state equation ax plus bu, and other terms are the same. In the place of u, I substitute here, I get this expression. So this is the equation I derived in the previous slide. We will collect all the terms to one side, we get this expression. Notice that every term has xk on the right hand side, so I pull it out. Now this is true for all x, so whatever is in the bracket should be equal to 0, so I get this equals 0. This is known as the discrete time Riccati equation. So we will start with the discrete time Riccati equation in the next slide. This is the equation we derived. We can take all terms from second onwards to the right hand side, I get this expression. Now let us define whatever is in the bracket here as m. So I get an expression for s of k, which is A transpose into this whole thing is m times A plus q1 from here. Now let us substitute for r, recall the expression for control effort we derived in the expression for m. In the place of r we will substitute this, so I get this m of k plus 1 equals s of k plus 1, which is this, minus s of k plus 1, which is this, b is there, r inverse, b into r inverse, and then b transpose s of k plus 1. And recall the boundary condition for s, we already derived this. If you go back you will see this written in red, so Sn equals q1. With this we are ready to summarize the control design procedure. It may be difficult to remember all the expressions, just go back and see whatever you have noted down that was written in red. you will see all the equations here. So this is the boundary condition, and recall Mk was this expression, and then we had the expression for control law capital K. We will store this control law, and then Sk minus 1 is obtained from here, and then K is reduced by 1, and this loop is repeated until K becomes 1. So these are nothing but collection of the equations we already derived. In case you do not remember these, it does not matter. You can always go back through the previous slides and see that these are indeed what we derived. With this, we will calculate the control law K once and for all. For example, we have K of K minus 1, K minus 2 and so on for this counter, whereas we also had K of capital N equals 0. We calculate this control law capital K, this index K equals 1, and use Uk equals minus control law capital K of K and Xk and determine control moves. We will now be able to derive the optimal value of the objective function also. This is our objective function J prime. We have this adjoint equation, we have the control equation. Using this, we will simplify this expression. We will substitute for lambda transpose K plus 1 into A from here. We will substitute this over here when we multiply by A. Similarly, lambda T K plus 1 into B from here. So let us do that. So J prime is the first one, nothing happens. This term also I write as it is, lambda T into Xk plus 1. Then I have lambda T into A, and lambda T into A will substitute and put these two, which is this, and lambda T times B, which is this, lambda T times B will be in the form of ut into q2, which is what we have, and of course there is a u here, I put that u here. Similarly, this xk comes here. Okay, let us start with that. Now we can simplify this. Notice that I have x transpose q1x, and here I have minus x transpose q1x. So these two will cancel each other. Here I have u transpose q2u, here I have u transpose q2u with a minus sign, these two will cancel. So I have only these two terms. So I have lambda t k plus 1 x of k plus 1, which is here minus sign, and this is lambda t k into x of k, and I have a half here. Now I expand this. Notice that the index k goes from 0 to n. When I expand and remove all the things that cancelled, I get this, namely at k equals 0 from here, and when I substitute k equals n, I get the last term here. All other intermediate terms will get cancelled. This minus sign term will cancel the plus sign term from here. And what is lambda of n plus 1? It is equal to 0. We derived this already. And so we arrive at the optimal index, which is nothing but half of lambda transpose 0 and x times. So what is the optimal index? It is half of lambda transpose 0 x 0. That means even when we start our control law application using LQR, we know exactly the best optimal index that we can arrive at, which is nothing but this. And in terms of lambda, recall that we called lambda as s into x. In fact, we anticipated and we found that to be correct. So this is the optimal index. To conclude, we differentiated the optimization index J prime. We simplified the resulting algebraic equations. This is a straightforward method, although little messy. We arrived at the discrete time Riccati equation. We solved the 2-point boundary value problem. We calculated the control law once and for all. Notice that this approach is different from the receding horizon control law we derived earlier, where we calculated the control law at every time step. Robustness is an issue in this because we calculate right at the beginning and use it throughout. Nevertheless, this is the basis for several other controllers. So this is a very important topic. With this, we have come to the end of this presentation. Thanks for joining. Goodbye.